first tech boom, agile systems helped organizations operationalize the product lifecycle. Then DevOps further optimized the production lifecycle and introduced a new element, that of big data. With more businesses now turning to machine learning insights, we are on the cusp of another wave of operationalization. So welcome to Machine Learning Operations. In this course, we are going to understand how to productionize the machine learning models in an automated, scalable, and optimized way. Some of the major topics that we will cover include Introduction to Machine Learning Operations, the DevOps for machine learning, designing data pipelines for scalability and optimizations using various tools and techniques, where we will build an end-to-end automated pipeline for virtual material testing. Evaluating the performance of a machine learning system will also be a part of this course. During the first tech boom, agile systems helped organizations operationalize the product lifecycle, flagging the way for continuous innovation by clearing waste and automating processes for creation. DevOps further optimized the production lifecycle and introduced a new element, that of big data. With more businesses now turning to machine learning insights, we are on the cusp of another wave of operationalization. Welcome to start the journey by understanding what is a machine learning operation, what does it really mean, and of course, there must be a solid reason to put our valuable time into understanding machine learning operations. So I will explain why it really matters to understand this thing. And the whole point to focus on in this course are design principles, not the actual development of machine learning models. Understanding the life cycle of a machine learning project can provide us a broader look at how different pieces of this puzzle work together at different stages. So that's going to be a part of this module. Let's get started. Before talking about machine learning operations, I want to mention this thing. Machine learning operations usually refer as MLOps. So we will utilize this term throughout the course. So let's try to understand MLOps. The word MLOps pulls heavily from the concept of DevOps. DevOps comes from two things, development and operations. DevOps have made it possible to ship software to production in minutes and to keep it running reliably. This approach has been so successful that many companies are already adept at it. So why cannot we simply keep doing the same thing for machine learning? Here's MLOps comes into the place. It combines two things, machine learning and operations. Despite the similarity of both concepts, MLOps is a different route. So let's try to understand that. Before describing the difference between DevOps and MLOps, let's see a bookish definition of MLOps. Machine learning operations is a practice that aims to make developing and maintaining production machine learning seamless and efficient. While MLOps is relatively young, the data science community generally agrees that it's an umbrella term for best practices and guiding principles around machine learning, not a single technical solution. Now, let's see how MLOps is different from DevOps. While both have been constructed on the same principle, machine learning and traditional software are fundamentally different. So there's one critical difference between MLOps and DevOps that makes the DevOps not immediately portable to data science teams. Deploying software code into production is fundamentally different than deploying machine learning models into production. While software can generally be developed locally with almost instant feedback on how a code change affects the end result. In machine learning, to see the effect of a code change requires retraining a model. Just imagine the difference between an application developer saving a code change and pressing refresh in their browser, and a data scientist saving a similar code change and then spinning up a cluster of GPUs, deploying code, transferring data, and training a model before seeing any results. While software code is relatively static, data is always changing, which means machine learning models are constantly learning and accommodating. The complexity of this environment, including the fact that machine learning models are made up of both code and data, is what makes MLOps a new and unique discipline. Machine learning operations is quickly becoming a critical component of successful data science project deployment in the enterprise. It's a process that helps organizations and business leaders produce long-term value and reduce the risk associated with data science, machine learning, and AI initiatives. Yet, it's a relatively new concept, so why has it seemingly skyrocketed into the data science glossary overnight? Data should always have a business focus. Operationalization helps to close the loop between gaining insight and turning that insight into actionable business value. A simple proposition, but not simple of an execution. Utilizing an MLOps approach could help your organization in different ways. Like operations team has the business knowledge, and the data science team understand the data. But what in between? A wide distance of mismatched expertise. MLOps combines the expertise of both sides for more efficient machine learning that leverages both sets of skills. As machine learning becomes more common, the regularity side of operations is a critical function, run afoul of regularity bodies, and it wouldn't matter how much insight you have learned. MLOps puts the operations team at the forefront of new regulations and best practices. They can take ownership of regularity processes while the data team concentrates on deploying creative models. The bottleneck that results from complicated, non-intuitive algorithms eases with a better division of expertise and bigger collaboration from operations and data teams. MLOps tightens the loop. By allowing safe and reliable operations, MLOps is key in mitigating the risk induced by the use of machine learning models. However, MLOps practices do come at a cost, so a proper cost-benefit evaluation should be performed for each use case. Machine learning operations isn't just important because it helps mitigate the risk of machine learning models in production. It is also an essential component to massively deploying machine learning efforts. Going from one or a handful of models in production to tens, hundreds, or thousands that have a positive business impact requires MLOps discipline. Good MLOps practices will help teams to keep track of versioning, especially with experiments in the design phase. It helps to understand why the retrained models are better than the previous versions, and even to ensure that model performance is not degrading in production at defined periods. The paradigm of MLOps has four main pillars as guiding principles. First one is the machine learning should be collaborative. When addressed from the prospect of a model or even machine learning code, machine learning cannot be developed truly collaboratively as most of what makes the model is hidden. MLOps inspires teams to make everything that goes into producing a machine learning model visible, from data extraction to model deployment and monitoring. It is very easy for a data scientist to use Python or R and create machine learning models without input from anyone else in the business operation. This might be fine when developing, but what happens when you want to put it into production and there isn't a unified use case? Collaboration must begin from day one, where everything is fully audited. Organizational-wide permissions and visibility will ensure strategic deployment of machine learning models, where everyone is aware of even the most granular of detail. Secondly, machine learning should be reproducible. Typically, machine learning models are designed to be unique. The core reason of this is that data doesn't tend to have a one-size-fits-all design. What is right for one business wouldn't work for another, as their data will give different insights. Data scientists should be able to audit and reproduce every production model. In software development, version control for code is standard, but machine learning requires more than that. Most importantly, it means versioning data as well as parameters and metadata, storing all model training-related artifacts ensures that models can always be reproduced. Having these attributes available is a vital part of MLOps lifecycle. Reproducibility straight away ensures we're dealing with a process and not simply an experiment. Third one is that machine learning should be continuous. Continuous integration and continuous deployment are vital for effective MLOps. This is the process of ensuring newly added code and data to start automated development and testing. The risk with machine learning is that it can lock data scientists down as their model have to be trained within a known technology stack. For machine learning, having flexibility is key to creating the right model. The lifecycle of a trained model depends entirely on the use case and how dynamic the underlying data is. Building a fully automatic, self-healing system may have diminishing returns based on your use case. But machine learning should be thought of as a continuous process, and as such, retraining a model should be as close to effortless as possible. Without continuous processes, data scientists will spend a lot of time creating manual and ad hoc models each time. And last but not least is that machine learning should be scalable and monitored. Computer power is fundamental to the machine learning lifecycle. Machine learning engineers need to have an infrastructure layer that allows them to scale work without needing to be an expert in networking. Volumes of data can grow very quickly, and data teams need the right setup for them to grow naturally. Monitoring is a part of engineering practices, and machine learning should be no different. In the machine learning context, the meaning of performance is not only focused on technical performance, such as latency, but more importantly, predictive performance. MLOps best practices encourage making expected behavior visible and to set standards that models should adhere to, rather than relying on a gut feeling. In reality, machine learning projects are not straightforward. They are a cycle iterating between improving the data, model, and evaluation that is never really finished. This cycle is crucial in developing a machine learning model because it focuses on using model results and evaluation to improve your dataset. Phase 1 of the machine learning project's lifecycle is the data. While the end goal is a high-quality model, the lifeblood of training a good model is in the amount and, more importantly, the quality of the data being fed into it. There are several steps related to the data. First, data collection. Collect as much raw data as possible despite of the quality. In the end, only a small subset of it will be annotated, because it is useful to have a lot of data available to add as needed when problems arise with model performance. Next one is the annotation schema. This is one of the most important parts of the data phase of the lifecycle, and it usually gets neglected. A poorly constructed annotation schema will result in an ambiguous classes and edge cases that makes it much more difficult to train a model. For example, the object size, density, orientation, and truncation can provide critical metadata for the performance of object detection models. Then we have the data annotation. Annotation is a tedious process of performing the same task on and on for hours at a time. This is harder to spot by the QA team of an annotation firm, and is something that you need to check yourself. Great. The next phase in the lifecycle of a machine learning project is the model. Even though the output of this process is a model, you will ideally spend the least amount of time in this loop. The first step in this phase is explore existing pre-trained models. The goal here is to reuse as many available resources as possible to give yourself the best head start to model production. Transfer learning is the core inhabitant of deep learning in this day and age. Several websites are providing pre-trained models like TensorFlow Hub and ModelZoo.co. The second step in this phase might be the construction of the training loop. Your data will likely differ in some way from what was used to pre-train the model. You will also need to modify the output structure of the model to match the classes and structure of your labels. PyTorch Lightning provides an easy way to scale up model training with limited code, so you can give it a try. Next step might be track the progress. This entire cycle will likely require multiple iterations. you will end up training a lot of different models, so being precise in your tracking of different versions of a model and the hyperparameters and data it was trained on will help a great deal to keep things organized. Next phase in the machine learning project lifecycle is the evaluation. Once you managed to get a model that has learned your training data, it's time to dig in and see how well it can perform on new data. The key steps for evaluating a machine learning model are following. First one is visualize model outputs. As soon as you have a trained model, you need to immediately run it on a few samples and look at the output. This is the best way to find if there are any bugs in your training or evaluation pipeline. Before running evaluation on your entire test set, choose the right metric. Coming up with one or few matrices can help in comparing the overall performance of models. In order to make sure you pick the best models for your task, you should develop matrices in line with your end goal, and also update matrices as you find other important qualities you want to track. Next one is look at failure cases. Everything your model does is based on the data that it was trained on. So assuming that it is able to learn something, if it is performing more poorly than you would expect, you need to take a look at the data. It can be useful to look at cases where your model is doing well, but it is vital to look at false positive and false negatives, where your model predicted something incorrectly. Next one is formulate solutions. Identifying failure cases is the first step in figuring out ways to improve your model performance. But in most cases, it goes back to adding training data similar to where your model failed. But it can also include things like changing pre- or post-processing steps in your pipeline or fixing annotations. No matter what the solution is, you can only fix the problems with your model by understanding where it fails. And the last phase in machine learning project lifecycle is the production. So finally, you have got a model that performs well on your evaluation matrices with no major errors on various use cases. Now, we will need to monitor the model. So test your deployment to ensure that your model is still performing as expected on test data with respect to your evaluation matrices. And also evaluate new data. Using a model in production means you will frequently pass brand new data through the model that it has never been tested on. It's important to perform evaluation and dig into specific samples to see how your model performs on any new data it encounters. And you must have to continue understanding the model. Some errors and biases in your model can be deep-seated and take a long time to reveal. You need to continuously test and investigate your model for various edge cases and trends that could cause problems if they were to be found by clients instead.